We begin this section with a very important point, and that is that primary structure determines secondary structure. Another very important point is exemplified in figure 6.3 of your book and was alluded to earlier. Namely, the peptide bond rotates as a plane, and therefore only certain angles, called phi and psi, are allowed in order to keep the ends of the molecules from colliding with each other. One additional point is that there must be bonds which hold the protein in its particular shape, and nature seeks to minimize that energy. For proteins, that bond is the hydrogen bond. If one plots the allowable phi angles on one axis and the allowable psi angles on the other axis, one can recognize that there are basically two places that are heavily populated by proteins. These two locations are the alpha helix and the beta sheet. There is a third structure that we will consider here, which is the collagen triple helix. So secondary structure is the localized three-dimensional shape. Shown here, I have a section of alpha helix, and what I have done is to label what we would refer to as one turn of the helix. In other words, what I have done is to choose a point and the next point where it repeats. That is one turn. The amount of distance traveled in that one turn is 5.4 angstroms. This corresponds to a number of amino acids of 3.6. In other words, there are 3.6 amino acids per turn. There are various reasons one might want to know that, such as to compute the number of amino acids needed to traverse a plasma membrane. On this slide, what I have done is to somewhat incorrectly draw two dipeptides in such a way as to represent a turn along the alpha helix. I have been highlighting, and I also highlighted two hydrogen bonds that would exist between those dipeptides. On the right-hand side of this slide, what I have done is an attempt to show 3.6 hydrogen bonds per turn of the alpha helix. The net of this is to demonstrate that hydrogen bonds are parallel to the alpha helix, and there are many different hydrogen bonds along the length of an alpha helix. This is what stabilizes the structure. Another very important point is where the R groups are located. I am here showing a view from the top of an alpha helix and show that the R groups protrude radially around it. And again, what I'm trying to show is that there should be 3.6 R groups in one turn of the alpha helix. Importantly, proline cannot be present within an alpha helix because it is in the imino amino, because it is an imino amino acid rather than amino acid. The peptide bond cannot rotate normally, and proline will always terminate the alpha helix. The second common secondary structure is a more extended conformation than the alpha helix. In addition, the beta sheet structure can either expand or contract. Consequently, we do not think about beta sheet as having a definite size as we did with the alpha helix. Wool is an example protein which exists in a beta sheet structure. And you may be aware that you cannot heat a wool sweater because it will shrink. Beta sheets do have a characteristic location of the R groups. As shown in my hand drawing, the R groups alternate above and below the plane of the beta sheet structure. See figure 6.13 of your book for a more nicely drawn structure. Unlike the alpha helix, all the amino acids can be present in a beta sheet. If you examine all of the proteins with beta sheet structure and tally which amino acids are used to construct the beta sheet, though, what you will realize is that for whatever reason, Mother Nature has a preference for certain amino acids. Like the alpha helix, the force responsible for the beta sheet is the hydrogen bond. However, in this case, the hydrogen bond is perpendicular to the axis rather than parallel to the axis. Beta sheets can be parallel or anti-parallel, which I have shown with a somewhat crude drawing on this slide. The directionality of the arrows is from the amino to the carboxy terminus. One more fact about, and what I have done is to illustrate the hydrogen bonds as the red lines between the arrows. One more fact about the beta sheet is that Mother Nature has decided that short beta sheets are better than long beta sheets. And the average, if we examine all known proteins, is 8 amino acid residues. The third secondary structure is the collagen triple helix, which I have shown in both ribbon and space-filling forms on this slide. You will notice that although the alpha helix was a very regular in its shape, the collagen triple helix is what I describe as kinky. The reason for the kinkiness is the existence of proline, or hydroxyproline, HYP, which again, because it is an imino amino acid, induces a kink in the chain. The second amino acid can be any amino acid, but the third amino acid of collagen is always glycine. This is because the hydrogen of glycine, the R group, can fit into the bend induced by the proline. To reiterate, the force that is most important in secondary structure is the hydrogen bond. There are other forces which influence secondary structure. For example, if lysines were present every 4 amino acids, it would disrupt the alpha helix. The reason for that is that we would have a positive charge lining up along one side of the alpha helix, and those positive charges would be repelling each other.